proper tuning of the weights ensures lower error rate, means lower loss, making the model reliable. So in our case, in our example, we just get our inputs. We are randomly finding out some kind of argument, some kind of weights and biases in order to generate the function which allows us to calculate our outputs. So we are taking this randomly at the first iteration, and then we're calculating the output. If the output is far away from the expected value, we know obviously the output value, then we are fine-tuning the biases and the weights, and we are making this calculation again, and we are doing this iteration as long as the output is very close to the calculated output, is very close to the expected output. So the backpropagation is just the way of propagating the total loss back into the neural network to know how much of the loss every node is responsible for, and subsequently updating the weights in such a way that minimize the loss by giving the nodes with the higher error rate lower weights, or vice versa. So the next, I would like to present you just a few very popular and very good data sets using for image classification. One of them is MNIST, which means Modified National Institute of Standards and Technology database, which is a very large database of handwritten digits that is commonly used for training various image processing systems. Another one is Cipher10, for example. The next very important, very popular, very big data set used for image processing, image classification is the IMAGENET. This database contains more than 14 million different kind of images, which are hand annotated. It means each image has a own label, and they are categorized in more than 20,000 different categories. You can see on the bottom of the slide the internet site there is a link to the site where you can find a list of almost all of the data sets which are right now using for the deep learning applications. So let's go then to the theory of the deep neural network. What is this actually? A neural network is a type of machine learning which models itself the human brain. This creates an artificial neural network that via an algorithm allows the computer to learn by incorporating new data. So while there are plenty of artificial intelligence algorithms these days, neural networks are able to perform what has been termed deep learning. While the basic unit of the brain is the neuron, the essential building block of the artificial neural network is a perceptron, which accomplishes simple signal processing, and these are connected into the large mesh of the network. Convolutional neural network is a different kind of neural network which is used very often for the image processing. So convolutional neural network, or we can also call it just shortly CNNs, are a category of neural networks that have proven very effective in areas such as image recognition and classification. CNNs have been successful in identifying faces, objects, and traffic signs, apart from powering vision in robots and self-driving cars. Channel in conventional terms used to refer to a certain component of an image. An image from a standard digital camera will have 3 channels: red, green, and blue. You can imagine those as 3 2D matrices stacked over each other, one for each color. each having pixels values in the range from 0 to 255. In grayscale, on the other hand, has just one channel. For the purpose of this training, we will only consider grayscale image, as you can see on this animation. So we will have a single 2D matrix representing an image. The value of each pixel is a matrix will have range from 0 to 255. 0 indicating black and 255 indicating white. CNN derive their name from the convolution operator. The primary purpose of convolution is, in case of the CNN, is to extract features from the input image. Convolution preserves the spatial relationship between the pixels by learning image features using the small squares of input data. In our animation in the slide, you can see the green matrix, which are slide over our original image by 1 pixel, and this slide is also called a stride, and for every position. Then we compute element-wise multiplication between the two matrices and add the multiplication outputs to get the final integer, which forms a single element of the output matrix. In CNN terminology, the green matrix is called filter or kernel or feature detector, and the computing and the image of the computing, the product is called convol feature or activation map or even feature map. It is important to note that filter acts as a feature detectors from the original input image. So this is how it looks in the practice. So we've got on the left side our original image, and on the right side we can see a few examples of the different kind of layers in the convolutional neural network after the filtering, after using the convolution, after using our filter, after filter, or in other words our kernel. So we can find out different kind of details on the on our picture, and therefore we are using the convolutional neural network. And actually in the machine learning, all of this is done for us automatically in order to find out different kind of details on the picture. So for the different kind of applications, we are using different kind of networks. So there are differences between them as just the architecture, how deep they are, how hidden layers between the input and between output layers, how many hidden layers we've got. Architecture itself is a difference. So on the right side you can see different kind of models, neural network models, they are using for different kind of applications depending of operations they can support, and also of the accuracy they can support. And here again a few machine learning task examples. Here is a classification when we've got some kind of, and at the input we have image and we are expecting as an output just the label. So we have to find out that on the picture, in this case we've got a cat. So for this kind of application we can use a different kind of architectures. A few examples here is a ResNet or MobileNet or the LeNet 5. Here we've got a machine learning task which is called detection. So we've got the input image, and as the output we are expecting the class label and the location of the object. So for this one we are using different kind of models like ResNet or Inception. In order to program, in order to create our neural network model, we have to give the information in some way. Today we can use a different kind of frameworks. Definition of framework is this framework is comprised of an interface, library or tool which allows developers to more easily and quickly build machine learning models without getting into the details of the underlying algorithms. And so right now we are using different kind of frameworks, different kind of software environments in order to build and program our models. The most popular probably today is TensorFlow. We are using also Caffe2 models. You can also see on the slide Torch and PyTorch. And very popular is also Keras, which is actually framework on the top of TensorFlow of the Torch, when we can using the Python or C++ in order to program TensorFlow or Torch. TensorFlow or Torch, there are frameworks which are pretty complicated if you have no experience, and with the Keras you've got access to APIs, you've got access to libraries which are much more user-friendly and allows to program the TensorFlow and use the different kind of neural network models. Python. Why Python is so popular in area of data science and machine learning? Python is a general purpose programming language that became very popular very quickly, mainly because of the simplicity and code readability. It enables the programmer to express ideas in fewer lines of code without reducing readability. Compared to languages like C or C++, Python is slower, but Python can be easily extended with C and C++. So it allows us to write very sophisticated and very computationally intensive code in C and C++ and create Python wrappers that can be used as a Python modules. That gives us two advantages. First, the code is fast as original C or C++ code, and the second, it's easier to code and read in Python than in C and C++. Again, why Python? There is a power of the libraries in the Python. So what I mean, you can use different kind of libraries like NumPy, which is comparable to the MATLAB. You can just use the pandas. You can just use OPENCV, which is a great library for the image processing, and all of very sophisticated and complex functions are actually done for you in the background, and you are just using one line of the code in order to run this. So one very popular and very important library in this case is OPENCV. OPENCV is a Python wrapper for the original OPENCV C++ implementation. OPENCV Python makes use of NumPy, which is a highly optimized library for the numerical operations with the MATLAB style syntax. All the OPENCV array structure are converted to and from NumPy arrays. This also makes it easier to integrate with other libraries that use NumPy, such as SciPy or Matplotlib. So there is just a very simple example how easy it is to make face or eye detector, in this case using OPENCV library. So you can see we just loading the image and loading the classifiers which are already done, and then with a few lines of code we are just finding out where the eyes are located in the image, and that's all. That's very fast and very simple way. So with OPENCV 3.3 version, this is also the new module implemented, this new module introduced, which is called Deep Neural Network, DNN module, and then you can use the trained model from the different kind of frameworks and the different kind of network architectures. On the slide you can see a few examples, but this is even more, and this is very easy way to use already trained model into your application. If we are talking about the Python, I have to also say a few words about the PYNQ. PYNQ is the Python on the Zinc. Zinc is a very well-known platform of the system on chip of XILINX. PYNQ is an open source project from XILINX actually that makes it easy to design embedded system within XILINX Zinc system on chips. Using the Python language and libraries, designers can exploit the benefits of programmable logic and microprocessor in Zinc to build more capable and exciting embedded systems. So you can see that there are a few layers in the PYNQ system itself. So there is an FPGA, programmable logic, and we can download and use our IPs, our bit streams. There is a drivers when we communicate between the Linux kernel and the programmable logic itself. There are APIs as usual on the Python, so if you are a Python programmer, you can easily use Python and have access to all of the resources of the system on chip in Zinc, and you can build on the top also your applications. So there are a few evaluation boards already available. You can see here 4 of them. There is also more planned, like for example ZCU 111, which is based on the radio frequency system on chip device of XILINX, but there will new also come when the Linux image is available with the PYNQ, and you can just start out of the box the programming resources of the Zinc using the Python. So what is the PYNQ? Just once again as a summary. PYNQ is intended to be used by a wide range of designers and developers, including software developers who want to take advantage of the capabilities of Zinc and programmable hardware without having to use ASIC style design tools to design hardware. Also can be used the system architects who want to easy software interface and framework to rapid prototyping and development of the Zinc design, and obviously hardware designers who want their designs to be used by the widest possible audience. What is also here mentioned, this is Jupyter Notebook, which also can be used by with the PYNQ together. Jupyter Notebook is just a browser-based interactive computing environment. Jupyter Notebook documents can be created, then include live code, interactive widgets, plots, explanatory text, equations, images, and video. A PYNQ enabled Zinc board can be easily programmed in Jupyter Notebook using Python. So this is very good starting point if you would like to start working with the Python and with the Zinc together. So the next is to give you a few words about the machine learning. XILINX offers an optimal trade-off of latency, power, cost, flexibility, scalability, and time to market. XILINX's unique pruning technology can provide up to 50 times network performance optimization, resulting in increased performance or frames per second and reduced power. So what is pruning technology? We'll talk a little bit later, but this is just a kind of optimization of the neural network when we can just remove the redundancy nodes and then make our network smaller, more compact, or more efficient. Low latency, this is a very important point. XILINX differentiates itself from the competitions by providing high throughput and low latency. Fast response times in critical applications requires the ability to provide high throughput without needing to execute large batches of images. With the XILINX solution, images are processed immediately, resulting in the lowest latency. The next very important point is that XILINX provides the ability to not only accelerate the deep neural network itself, but the entire applications, including performance, critical functions such as pre-processing, post-processing, and co. So you can build your complete application, not only acceleration of artificial intelligence in one device mostly. Flexibility of architecture. The flexible architecture that XILINX provides allows to perform the quickly adapt to evolving precision, evolving algorithms. So the neural networks architecture are still growing, are still there are still new architectures coming each years, and the existing one are still evolving. So with the FPGA, with the architecture, you have the possibility to adapt it very fast. So this flexibility of FPGA is in this case very important point. XILINX is continually improving its artificial intelligence IP and tools, resulting in increasing performance and reducing powers. And an edge AI platform based on XILINX immediately benefits from this improvement. So XILINX provides a truly scalable solution for AI inference, from Zinc 7000 family to the Zinc UltraScape Plus or MPSoC. The XILINX Edge AI solution can scale to meet the needs of virtually any artificial inference. On this slide you can see the overview of the machine learning flow. There are two phases in the machine learning. The training one, when we are using the powerful GPUs and different kind of software frameworks like TensorFlow, Caffe, and then we are establish our neural network and we are trained the neural network. When the architecture, when the model is done, is trained, we can use it further and inference, implement this model into our edge device, in our embedded device. So we have the solutions I would like to present you, solutions when we can use together with XILINX in order to implement these models very quickly and very fast and very efficient in the end in FPGA system on chips of XILINX. There are three main parts of XILINX edge solutions. The first one is DNNDK, Deep Neural Network Development Kit. So this is a set of different tools which allows us to translate the data from the originally trained model and implement it to the model into the edge, to the embedded device. The second very important part is a deep learning processing unit, which is IP, which is implemented into the programmable logic part of the system on chips of XILINX. And the third part is the hardware software platform for deployment. This flow, this slide is very important because it's showing you how the flow works in general. So starting from the left, we have the TensorFlow or Caffe framework when we are training our model. So for that we are using the 32 floating point data which are supported by GPUs, and after the process of training we've got our model. So we're taking this model and we are starting the DNNDK flow, Deep Neural Network Design flow from XILINX. This is in the middle. You can see the pruning step is the first one, which is the optional. Pruning, as mentioned already, is the optional step which allows us to reduce the redundancy and optimize our network. Actually, this is the retraining our network, which is pruning is quite timing consuming step, and this is very powerful also tool, but as I mentioned, this is a optional step when you are using the DNNDK. The next step is quantization, which is actually translation from the 32 floating point value from the training to the 8-bit integer value, which will be then later used by the DPU IP. And then we have to compile our model, which will generate executable file, which will be then understood by DPU itself. The last step on the very right side of the slide, you can see this is the mostly the standard Vivado flow when you can just make your hardware design. When you're putting all of the needed blocks using the Vivado, you have to obviously instantiate DPU. And then you instantiate also different kind of interfaces, and then you are building the PYTHON with support of PYTHON. We are building your Linux image, and then you have ready to boot image in order to use with the Zinc device. So once again, the first phase, model development and training using the Caffe TensorFlow, and normally done on GPU machines. You can use it your GPU on your own server, or in a lot of cases you can also running on the cloud. And the second step is the model compression with Descent. Descent is a one of the tool which is a part of DNNDK, and you can see in this flow here from left to right that we are taking, as mentioned before, floating point unit data from the training phase. We are making the pruning, fine-tuning, then making the, which is, as I mentioned, optional. They are making quantization, which is converting data to the integer 8-bit values, and then we are going to the compilation. What is DPU? DPU is Deep Learning Processor Unit, and this is IP which is which should be implemented into programmable logic side of the Zinc. The unit contains register, configure module, data control module, and convolution computing module. There is a specialized instruction set for DPU which enables DPU to work efficiently for many convolutional neural networks. The deployed convolutional networks in DPU includes VGG, ResNet, GoogleNet, YOLO, SSD, and so on. The DPU IP can be integrated as a block in the programmable logic side of the selected Zinc devices, with direct connections to the processing system. To use DPU, we should prepare the instructions and input image data in the specific memory address the DPU can access. The DPU operation also requires the application processing unit to service inter-apps to coordinate data transfer. Here, once again, overview of the solutions supported by XILINX. So on the right side, you've got the edge, which we are already talked about, like and with support with DNNDK and DPU, you can implement the neural network on the different kind of Zinc devices. And on the left side, you've got the cloud, where with support of the, for example, Alveo cards, you can also implement in very effective way your machine learning algorithm. What is Alveo? Alveo is a data center accelerator card designed to meet the constantly changing needs of the modern data center, providing up to 90x performance increase over CPUs for common workloads, including machine learning inference, video transcoding, and database search and analytics. And here the last slide, where summarizes the flow and the platform of the XILINX artificial intelligence. So what we support is the silicon. So there are the different kind of zinc devices. We also support our customers with different kind of boards which are ready out of the box, and you can just implement different kind of neural networks on them. We've got the software with the DNN-DK, and we've got also the different kind of models, which calls here Model Zoo, where also out of the box, directly from the shelf, you can take different kind of pre-trained models for detection or classification, and you can use it just as I mentioned right now without the working and on the training phase, which save the customers a lot of time. And on the top you can see the frameworks which are currently supported by the DNN-DK, which is CAFE or TensorFlow, but development of this complete flow XILINX is still running, so please stay tuned and you will see very soon the new solutions and the new supported networks and frameworks as well. So thanks again for your attention. This is just the summary and the link to the site of XILINX, when you can find out a lot of interesting information, useful information about the machine learning and artificial intelligence and deep learning, all about the inference, how to implement your models on the real devices. And I think this journey started for all of the customers and is really interesting and good points to also start it right now. So please let me know if you have any questions. My name was in the first slide, so don't hesitate to contact me if you have any further questions regarding the topics which were discussed today. Okay, so that was the last slide. Thank you for your attention. I just see there are 3 questions which I would like to answer. The first one is what is the flow for the cloud and for the edge the same? Can we use the same DNN-DK flow for both? So this is a very good point, because what we covered during this presentation was the DNN-DK flow design, the deep neural network development kit from XILINX. Last year, XILINX announced the completely new software design flow, which calls VITIS, and part of the VITIS is also VITIS AI, VITIS artificial intelligence. Actually, this is based exactly on the same as a DNN-DK. So we've got our pruning tool, which is now called optimizer. We've got our quantization. We've got our compilation. So the flow is actually the same, but is common for the cloud and for the edge devices. So you can use exactly the same kind of commands for the Alveo cards, which you can program with the host computer over the PCI Express, or you can use the standard FPGAs, standard system on chips like Zinc or MPSoC. So VITIS was, as I mentioned, announced last year, and right now in March we had already the second the update of this, the second generation, the version 1.1, actually, when the still new features are added. Like, for example, TensorFlow 1.12 right now is supported. So you can just take the train model from the TensorFlow from CAFE or CAFE2, translate it, and then place anyway in Alveo card on in any, not any, but in appropriate XILINX device. So if you need more information, you can visit obviously the XILINX site. Just search for VITIS AI, and this tool is completely for free, except of the pruning tool, which is the retraining. This optimization of the train model. But the rest is obviously totally free. You can use it, you can test it. There are a lot of models already available for the customers. There is a huge data bank which is called Model Zoo, and with Model Zoo you can just download the pre-trained model for a different kind of applications like face detection, face recognition, and just use this model for your application. So without any special fee. And as I mentioned, this tool is completely free with one exception, with the optimization, with the pruning tool, which is actually optional and you don't need to use it. This is just optimization of the speed and of the area of the network itself. So the next question is there any plan to realize 4-bit quantization? Right now, as I mentioned, after the training, when we are training the model with TensorFlow, for example, we always have a result with 32 floating point bits data, which was always difficult to historically for FPGA to translate floating points in the FPGA world. Therefore, there was a quantization which we presented to the 8-bit. So this 8-bit is a very good compromise because we can achieve less power, less area, and much more speed realizing the model with very less drop of the accuracy. So this was, as I mentioned, very good compromise, but there will be possible also in the future to use different kind of granularity of this quantization, like 4-bit or even 1-bit. There are also 1-bit neural network available, which are obviously very fast, very consuming much less power, but they are also slightly little accurate as the standard 32 bits. And you can also mix this in the future. It means you can for the critical first and second layer use the 8-bit, and for example for the another hidden layers use a 4-bit in order to optimize your network on the edge. And the last question is DPU architecture with this IP deep neural network processing unit optimized only for CNN, for convolutional neural network? Actually, right now, yes, it was designed for the CNN at the beginning, mostly for the image processing, but there are also the DPUs available for LSTM, long-term memory, where we need, for example, application for the speech recognition, and also the special DPU architecture for the random forest architecture, and there will be still more and more. So this architecture is still growing and growing. There are different flavors, different versions for the different kind of XILINX devices. For example, we are using different DPU version for Alvaro card, different one for the Zinc itself. But as I mentioned, with Vetis II flow, you can use it. In the same flow as I mentioned. And the last question, what I see, is there any way which you can self-education, which is my advice to get more information about it? Sure. There are great tutorials and great documentation on the XILINX side, on the GitHub. So if you would like to work with the inference side from XILINX, you can also visit the XILINX itself. If you would like to start with the theory of machine learning, with the artificial intelligence, I will probably point you to the Coursera or to the Udacity or to the LinkedIn Learning portal, when you can find out a few courses on the Coursera. There are some courses which are completely free, and there are very good courses, trainings regarding the theory of the machine learning, artificial intelligence, deep learning itself. And with Udacity, unfortunately, you have to pay for this, but there are also very good tutorials, very good courses how to go through the TensorFlow, for example. There are some examples step by step how to work with TensorFlow. So as I mentioned, I will then look at the Coursera, Udacity, or LinkedIn Learning portal when you can find out a few very interesting courses about it. So I believe that was the last question. I would like to again thank all of you for the attention, and if you have any further questions, you can just contact EBV, drop me an email, contact me over LinkedIn, and once again, thank you.